Hi, chemistry students. Let's continue our discussion about gases, and we'll pick up where we left off. We're discussing the Maxwell-Boltzmann distribution because it'll help us with what we're going to move on to today. Most importantly, we need to remember that the temperature was defined in the kinetic molecular theory to be related to the average kinetic energy. So if we have two different gases of different mass, the larger mass will have a smaller or slower average velocity. Notice this average, it's very important. So on average, heavier molecules move slower. We can see that in the graph that there's more. This dotted line here represents the heavier molecule, that it must be moving on average slower. As you see, there's a lot less molecules moving fast than there are moving slow. Knowing that, we can now think about an experiment we might be able to do to separate molecules out based upon how fast they move. And one way to do this is called a gas chromatograph. Now, I'm not giving you the full story here. We'll learn more about that later. But it does bring up an interesting idea. So the whole concept behind the gas chromatograph is we're going to put a gas or a liquid of some sort we're going to inject it into a system. And it's going to be pushed along by a carrier gas, normally something like helium, which doesn't react with anything. So this gas is now going to be moving around this long column filled with some chemical on the inside. So, but if this is an ideal gas, the ideal gas won't care what's in that column because it doesn't interact with anything. All it does is bounce off of things. So let's imagine that we're dealing with an ideal gas when we make our decisions right now. So if that's the case, everything that's in this container is going to have the same temperature. We would expect then that heavier molecules would move slower through the column and therefore take a longer time to get through. They would then hit a detector at a later time, and we could see this as a graph called a gas chromatogram. So just to give you an idea of what that looks like, here's a fake spectra of A, molecule B, molecule C. We get three different peaks. There's three different gases in this container. The question is, how would you rank them from low to high molecular mass? So notice the graph. It's a signal, how much stuff is hitting it, versus time. So this is often called the retention time, and it takes a little while for the molecules to get through there. If you remember, what we said was, as the molecular mass increases, the average velocity will decrease, so it's going to move slower. C then would have to be the heaviest one. It moved slowly, therefore it took more time to get through. Now there's another question. Were equal amounts of the liquid added to each mixture? Well, on the previous slide, I mentioned, and I didn't say it, but it's written down, that the area that this thing takes up is a representation of how many molecules there are. So the bigger the area, the more molecules of that type there are. Well, if we look at A and B, B is definitely shorter, but it's a little bit wider. So the area is always the base times the height. So A and B are roughly the same. C, on the other hand, is much shorter, but it's much wider. In fact, I created this gas chromatogram with this simulator, and A and B are exactly identical, and C is exactly 1/2 of A and B in terms of its composition. So just so you can see that written down, here's the same explanation. So we now have an idea about this gas chromatogram. Let's try to run it with some real molecules. And the molecules we're going to use are butanol and diethyl ether. If you take a look at these, here's what's something that's interesting. They have the exact same formula, but a different structure. They're called isomers. So if you ever hear the word isomer, it means that they're the same formula, so they have the same molecular mass, and the only thing that differs is how those atoms are bonded together. All right, that being said, assuming we run these through the GC, the gas chromatograph, how do you think they would have, how would the retention times actually relate to each other? And I'm hoping that you immediately think to yourself, you know what? That's the same molecular mass. Therefore, it should be the exact same retention time. And if they were ideal gases, that would be the case. However, let's look at what would really happen. In reality, we get two different peaks. So something's up here. And so what we've just found is that the kinetic molecular theory, which we've kind of used to guide us, there must be some errors in it. And we're interested in what those errors are. So First and foremost, these two gases have the same molecular mass, and if they're acting differently, that means that the structure must matter. Remember, that was the only thing that was different, is their structure. All right, so that means that they really aren't spheres at all. It also means, as we see this, that there's more to the story than just having a different structure. The structure must change how it interacts. These molecules interact with the chemicals that are pasted or placed on the inside of that column. There could be attractive, there could be repulsive, or there could be both types of forces working. So that brings up the question, how would we then modify the ideal gas law to take into account the possibility of these attractive and repulsive forces?